Hey everybody, welcome back to CSE 1322. In today's lecture, we're going to talk about some more recursion examples. So this is module number 4. This is part 3 of module number 4. So the first thing that we're going to talk about is that while you have seen a lot of recursion examples that deal with numbers, like the first one we did in lecture was to talk about factorial, and then after that we talked about raising something to a power, those are all dealing with numbers, and certainly numbers are a good use of recursion. There's lots of mathematical formulas that you can write recursively. But recursion is not limited to just dealing with numbers, and so we wanted to show you some examples that have to do with letters or characters or strings. And so the first example that we're going to do today is to take a string and reverse the string. So to be clear, we'll write a method called string reverse. It's going to take in a string such as A, B, C, D, and what it's going to do is it's going to reverse that string and return DCBA, the reverse of the letter order. All right, so let's talk about how we would go about solving this. So the first thing we're going to have to do is figure out our base condition. So what is the simplest string that we could be passed that we would know how to reverse? And the answer in general is it's going to be something at one end or one extreme. When we were dealing with numbers, it tends to be what happens if we ask for something raised to the first power or to the zeroth power? It's going to be a very small number, or a very big number is going to be the other option. So let's talk about a string. So what's the smallest string we could be asked to reverse that we would implicitly know how to do? Well, there's two valid answers here. One of them is you could say a single character. To reverse it, you just simply return the same single character. The other option is you could have no characters, a string that's just empty, in which case the reverse of that string is just an empty string as well. So one character or zero characters, either of them will work. For the purpose of this example, I'm going to do one character. All right, so then the next thing we have to figure out is how this algorithm is going to work recursively. So I'm going to flip over to a different screen here. And what we're going to do is we're going to take a look at an example string. So let's assume that we're passed in the string A, B, C, D, and we're asked to reverse that string. So what we're going to need to do is we're going to need to take the first character, and we're ultimately going to need to move it to the end. But before we do that, we need to reverse all the remaining letters. So if we reverse DCB and then we put the A at the end, it would be correct. So how do we do that? Well, we reverse the remaining part of the string first, and then we move the letter over. Well, how do we reverse a string? That turns out to be the method that we are writing. So effectively, we're going to tell it, you're going to reverse BCD, and then you're going to add to the end of that the A when you're done. All right. So how do you reverse BCD? Well, it's the same answer. We're going to call reverse with CD, which is the last two letters, and then we're going to eventually add a B to the end of that. All right. So how do we do that? Well, we're going to reverse just D, and then we're going to add a C to the end of that. Okay. Now, when we call reverse D, we know that that's our base condition, and the answer to that is simply the string D. All right, so now we are going to work our way back up the stack and do all of the remaining things that it told us to do. So we started off with D, and to that we're supposed to add C, and then to that we're supposed to add B, and then to that we're supposed to add A, and so you can see we get DCBA, which is what we were supposed to get. So that's how we're going to reverse the string. So let's look at that in some code. So we're going to hop over to an IntelliJ window here, and I'm going to create a new method. So public static, because I'm in my main class, it has to be public static. This is eventually going to return a string, and it's going to be called reverse string, and it takes in a string, which we'll call the string. Run out of imagination here. All right. So our base condition is the first thing that we're going to write. That's always going to be the first thing you're going to write. So our base condition was if we are asked to reverse a single character string. So if the string dot length is equal to 1, you're simply going to return the string because that's what we got. All right. So if you ask me to reverse A, the answer is A. Let's test that real quick. So what we're going to do is I'm going to make a string. I'm going to set it equal, I'll call it my string. I'm going to set it equal to just an A. And then we're going to call Um, answer is equal to reverse string, and we're going to pass it my string. And then we'll print out answer. Probably not answer in double quotes, just answer. Okay, so let's run this guy and see what we get. I have an error here. It's telling me I'm missing a return statement. Okay, since that return statement is in an if, it's possible that that if never fires. So it's requiring me to return something. I'll just return error, which we'll deal with that later on down the road. Okay, so let's try it again. And it says the reverse of A is, well, A. So, yay, my base condition works. It's important when you're writing code to always take a moment and execute each bit as you run it, just to make sure that it's actually working. It's easier to debug this now than when you've got 50 lines of code in there. All right, so assuming that you're asking me to reverse something that's bigger, let's go back over to my little whiteboard app and let's talk about what we did. So we need to call reverse again on a subset of the string. I need to remove that first character out of there, and then I eventually need to add the character back in at the end. So we're going to have to remember some string functions here real quick. So we're going to return reverse string, which is the recursive call. That's me calling the method that I'm currently in. And what I need to send it is everything but the first letter. Well, it turns out that I do that with the string dot substring, and I pass it the number 1. Now, if you remember what substring does, and you can always look this up, right? Java string substring. If you look that up, you'll get, well, an AI overview, which is probably quite helpful. But then down here, you'll see what it tells you is you pass it a start and an end. The start is where you want it to start returning the string. And since the string is indexed from 0, passing it a 1 means it gives me everything but the first letter in the string. So that's why I'm doing a substring of 1 there. Okay, and then to the end of that, I'm supposed to add back in the first character. So that's going to be the string at car at 0, which is the first character in the string. Car at is not spelled like that somehow. There we go. Sorry, I put in a square bracket. That was wrong. All right, let's clean that up. There we go. Okay, so to review, I make a recursive call and I pass it everything but the first character in the string, which is what I was doing here. And then I add to it the first character in the string, but I'm adding it at the end. And I'm just doing a plus here because remember with strings you can do plus and that just adds strings together. I'm just mushing the last letter onto the end. Okay, this return statement is now redundant, so I'm going to get rid of it. And we're going to test it again. So we'll test it with something simple. So I originally gave it A, let's give it AB, and let's run that and let's see if we get BA. And indeed we get ba. Ba. All right, next off, we're going to pass in a C, and we're going to run it again, and let's see how we do. CBA. Okay, so it looks like it is working pretty well. Let's give it a much bigger, longer one and make sure that it still works. And HGFEDB or CBA. Looks like it works pretty well. So that's how you go about solving something. And it's important to realize that here's the code in the slides just in case you want it for later on. It's important to realize that recursion is not just for numbers. You can use it for strings, you can use it for anything else. And so there you go, that's a string version. All right, so the next thing we're going to look at is, well, what about arrays? Can you use it for an array? So assume that you're passed an array of integers. How can you use recursion to sum the values in the array? So again, let's start off and figure out our base condition. So while we're figuring out the base condition, I'm going to go ahead and start writing up the basics of this. So I'm going to make a new project here. And so basically what we want is example 2. Great. This window. What we want to know is what's the simplest case of an array that we would inherently know how to sum? Well, let's make an array. So int my array is equal to new int, and then let's put some numbers in there. 1, 2, 3. Okay, so that's how I make an array, and that has 3 numbers in it. So the question is, what's the simplest array I could be given that only has let's say, one number in it. And if I was able to add that up, then I would know that it's just whatever that value is. So if you gave me an array that just has the number 7 in it and you asked me to sum the array, well, the answer is 7. So that sounds like a base condition to me. So we're going to do public static sum array, and sorry, it's going to return an integer. Um, and so we're going to have to pass it in an integer array. We'll call it the array because I'm very creative today. And our base condition is, well, so the answer would be if the size of the array is 1, but that means that I'm going to have to cut the array each time that I send it. And if you're coming from Python, that's actually really easy in Python. You can just send it a subset of the array using a slice. But Java doesn't really do that. I mean, it has methods for doing that, but they're not particularly intuitive. So I'm not going to do that. What I'm going to do instead is I'm going to pass it where I am in the array. So in addition to passing it the array itself, I'm going to pass it a position, and that's just going to tell me where I'm looking in the array. So every time I make a recursive call, I'm going to get the whole array, but I'm also going to get a position that's going to tell me, where I currently am actually looking in the array. So if I erase my board here real quick, let's draw out what it is that I'm showing you. Um, Ooh, which seems like there should be a faster way to do this. But anyway, here we are. Okay, I think I've gotten all the marks now. All right, so we're going to draw an array, and the array has, let's just say, 5 cells. We're going to put in the numbers so that we remember which cell is which. And then into the cells, I'm going to put 2, 4, 6, 8, and 10. Okay, so what I'm saying is each time I make the recursive call, I'm going to pass the array, which is what this is. So I'm going to get the whole array each time, but then I'm also going to pass in a position, which is going to tell me where I'm currently looking in the array. So when the position is, that says position. That is terrible writing. Having a hard time writing on the screen today. All right. So when I pass in a position of 0, that means that I'm currently looking at cell 0. When I pass in a position of 1 or 2 or 3, I'm currently looking at cell 1, 2, or 3. All right. So how would I know that I have an array with only one element in it? Well, it would be that the position is equal to the size of the array, right? Because if the size of the array is 1, and I'm looking in position 0, so I do need to subtract 1 from it, then that would tell me that I'm dealing with that. So let's go back to my code and let's update my if statement here. So I'm going to say if the position is greater than or equal to the array dot length minus 1. Okay, so the array length, assuming that I have an array that has one element in it, array dot length is going to be 1. And 1 minus 1 will give me 0. And so if my position is equal to 0, then that means I'm in the last cell of the array. All right, so in this case, I'm going to return the array at position, whatever position that is, probably 0. All right, otherwise, we know we're going to have a recursive call. So we're going to return some array, and we know that we're going to pass it the array, and then we know we're going to pass it position. But something's probably going to happen here with position. So I'll leave a couple of question marks in there. And then I may need to do some other stuff out there. So what I'm telling you here is every time you go to write a recursive method, you've got to figure out the base condition, which I just did. And then you've got to figure out the recursive call. And I know the recursive call has to pass the parameters that it requires. So I know it has to pass an array and a position. And then I have to decide, is the array changing or is the position changing? Well, if my base condition is based on the position changing, then the position needs to change each time. And so specifically, the position needs to be getting bigger because I'm checking to see if the position is less than the length of the array. So each time I call it, I'm going to pass it position plus 1. And then at the end here, I need to do something else. So I need to take, let's go back to my little picture of the array. So basically what I want to do is I want to take this number, which is 2, and I want to add it to the sum of the rest of the array. Right? So I want to take the sum of the rest of the array, which is this, which I don't know the answer to it, and I want to add the number 2 to it. And so eventually, when it calls sum recursively, it's going to give it 4, 6, and 8. So that's going to say, well, add 4 plus the sum of the rest of the array. Well, it doesn't know what the sum of the rest of the array is. So that's going to say, okay, well, then in that case, add to that 6 plus the sum of the rest of the array. And then eventually it's going to say, add to that 8 plus the sum of the rest of the array. And then it's going to say, okay, add 10 plus the sum of the rest of the array. But here's the tricker. What's the sum of the rest of the array here? Well, if we're passing it in 10, then this is 0. So now all of a sudden it can say, okay, it's 10 plus 0, which is equal to 10. And then that value is the answer to this question. So now it's 8 plus 10, which is 18. And that value is the answer to this question. So now it's 6 plus 18, which is 24. And that value is the answer to this question. So it's 4 plus 24, which is 28. Ran out of space. And that's the answer to this question. And then we're adding 2 to that. 2 plus 28 will be 30. And that's the correct answer. If you add up 2, 4, 6, 8, and 10, you indeed get 30. So that's how this is going to work. And so back over in my code, I need to take the current cell, which is the array at position, and add that to the sum of the rest of the array. Now, I certainly could have put this at the beginning or at the end. I could certainly put this over here and it would work the same. I'm just putting it at the front because that's how I did it in my example just a moment ago on the screen. All right, so as usual, let's test this. So int answer is going to be some array, and then I pass it my array, and I pass it as 0 because I want it to start in position 0, and then I'm going to system.out.println, and I'm going to pass it answer. All right, so if all is good, this should output the number 30 because the sum of all those is 30. Well, it looks like all is not good. I got 6. Okay, so what did I do wrong? Well, I passed it in the array and I passed it position plus 1, and I added into it the array at position. That all seems reasonable, and I'm checking to see if the position is greater than the array size minus 1. Okay, so honestly, I don't know why this is wrong. I just wrote code and it's not working correctly, so I need to figure out what's going on with it. So the way I'm going to figure it out is I'm going to add in a couple of print statements here. So I'm going to just tell myself I've been called with position and then plus position. All right, so this will allow me to see each of the calls. So I'm running it again, and it says I was called with position 0, I was called with position 1, I was called with position 2. Now that's odd. Oh, wait, hold on. The array that I'm testing with has a 1, a 2, and a 3. 6 really is the correct answer. All right, I was thinking that it was the bigger example that I had done on the board, and that's why I was thinking it was wrong. So that proved to me that I was called 3 times, position 0, position 1, position 2, and that allowed me to see that I actually was only running 3 times. All right, so let's add in 4, 5, and 6. Now, what did I have in the example? I had 2, 4, 6, 8, and 10. All right, now let's run it. With any bit of luck, we should get 30. There we go. I was called to position 0, 1, 2, 3, 4, and we did end up with the number 30. So it seems to be working correctly. All right, so again, the important lessons here are recursion is not limited to just numbers, although this is a number example, it also uses an array. The other thing to mention is that don't be afraid to add in a print statement so that you can see what's happening in the code. It's a real easy way for you to see what's going on. Like, for example, you could put another print statement in here that I reached the term, let's say the base condition with position. And now you're going to get a little bit more output, and it's going to tell you when it hit the base condition. I reached the base condition in position 4. And then you can look here and say 0, 1, 2, 3, 4. Okay, that makes sense. And you could add in print statements here that will show you each of the recursive calls and what it is that you're sending it. Okay, so hopefully this is a Fairly easy thing. You will find that when you're watching me code, it's going to make a whole lot of sense to you. You're like, oh, yeah, I totally get what he's doing. And then you're going to sit down and try to actually code this yourself, and you're going to have a really hard time. Just remember the three steps. Step one, find the base condition. And yeah, that can take a moment to figure out, but once you've found the base condition, write an if statement for it. Step two, figure out what your recursive call is going to look like. It's going to have whatever parameters that you need to have to yourself. And then step three, make sure that your recursive call is moving you towards your base condition. If it is, life is good and you're going to end up with a good program. All right. There's one last thing to say here, which is I asked you to write a method that takes in an array and returns the sum of the array. And what I ended up writing here was a method that takes in an array and a position and then returns the sum of the array. So every time somebody calls my sum array, they have to remember to pass a zero here. And if they don't, it's not going to work because it requires two things to be passed in. That's not really ideal. There is an advantage of this, which is if I wanted to sum from the third position in the array, I could pass in the number 2 and run it. And when I run that, it's going to skip cells 0 and 1, and it's only going to add the 6 and the 8 and the 10, which of course is 24, 2, 3, and 4. So that's kind of a cool extra function, but it's not really what I asked them to do. I asked them to just take in an array and sum the array. So in order to make that work, I need another version, another overload, shall we call it, of sum array. So I'm going to make another version of sum array that just takes in the array. And then all it's going to do is it's going to call sum array, passing it the array and the 0, which is what you need to do in order to start it off at position 0. So now down in main, they can call my sum array without having to pass it the 0, and it will automatically do it. So they now have two versions of the array, or sorry, of the method. One version that just automatically assumes you're indexing from 0, and another version which allows you to specify where you want to index from. So now I've actually built something that's better than what was asked for. They have both options that they can use. This is referred to as a helper function. And really all it's doing is it's just calling the other one, but it's passing the parameter that I needed everybody to always pass. So this is a little trick to keep in your back pocket because every now and again, this is super handy. Remember, this is just an overloaded method. The definition of an overloaded method is you've got the same name, but you've got different parameters that are coming into the method. So that's an overloaded method. So that's a little aside. Coming back over to our slideshow here, this is the slide that was asking us to make this sum array. This is just the same code that I just did a moment ago on the other screen, just so that you have it printed out in the slides. And then this just mentions the helper method that I just explained to give you that. Okay, so why are we doing recursion? It seems like it's more complicated, it's less intuitive. It seems like it has this weird problem that sometimes if you pass it a big enough number, it's just going to give you a Stack Overflow. It seems like it crashes worse. And I'm also going to confess to you that it uses more memory than a loop would have. And for all of these problems that we've given you so far, you could easily solve them with a loop. Like, certainly power is very easy with a loop. You just iterate multiple times and you add the first number or you multiply the first number by itself. That's really easy with a loop. And reversing a string, well, first off, there's a built-in method that does that. But ignoring that, there is, it's a pretty simple thing to do that. So why would you do it with recursion? And the answer is that, and I've said this before at the beginning of this section, all of these are very simple problems that we're asking you to do. They're good for learning how to do recursion, but they're not actually real world problems where you would use recursion. Truthfully, for all of these linear problems that we've given you so far, you would pretty much use a loop. They're going to be more efficient, it's going to work better, but we want you to be able to understand recursion because from here on out in this presentation, I'm going to talk about more advanced problems that are going to use recursion, and recursion is really the best way to solve it. So without further ado, let's take a look at this question. So on your computer, you have, there's an equivalent in Mac and Windows, but you have a little file explorer. And so if you bring the file explorer down onto your desktop, let's see here. Yeah, there we go. Okay, so here's my file explorer. I opened it here, and pretty much what we have is a bunch of files that are in a folder. And you know that inside of any given folder on your machine, you can produce other folders. So, like here on my desktop, I can right click and I can do new folder and I can call it test folder, or I can call it whatever I want. And over here in my documents now, if I look at my desktop, you'll see that I now have this test folder. And inside the test folder, which is this, I can create a new folder. And I can have them as deeply nested as I want it. So in my new folder, perhaps I might have lab 1, and then I might have another folder for lab 2, and another folder for lab 3. And I can keep making folders, and then inside of lab 1, maybe I have, you know, a folder that keeps track of the question, and then I could have a folder that keeps track of the answer. And I could do the same thing in each one of my other um, folders as well. Okay, so you're hopefully familiar with the idea of folders. The question is, if I asked you to write a program that could go through all of your folders on your machine and count how many items you have, how would you go about doing that? And the answer to that question is, well, it's quite simple to explain, but it's actually a whole lot of work. So remember that your computer, whether you're a Mac or Linux or Windows, you have the beginning of your file system. In Windows, it's called C colon in most computers. So that's the beginning of the file system. It's the top level, effectively. In a Mac, it's going to be slash, and likewise in Linux. So that's the start. And inside of that folder, you can have files and you can have other folders. And so each of those subfolders can then have files in them or they can have folders in them. So for example, my C drive here, it has the following things. And if I open up users, you can see there are two folders inside of users, one for eSol E13 and one for default user. And so inside of eSol E13, there's my desktop and my documents and all of those folders inside of there, and so on and so forth. So the answer to how many files do I have on my computer is count how many files are in the root of the file system. So start off all the way down here at C colon, count how many files, which it looks like it's 2 here, and then go into the first folder and count how many files are in there, and then go into its first folder and count how many files are in there. Well, okay, so that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Looks like 14, 15, 16, 17, about 18 files in here. And none of these are folders, they're all just files. So now I've completed that, I would go back up one folder to the app folder and I look for any more folders in there, which there are none. And then I go back up to the C, and now I got to do the same thing in the Dell directory. And in there, I've no files. In here, I've no files. In here, I've got 3 files. And then I check to make sure there's no other folders, check to make sure. But it's possible that when I go into a folder, there may be many subfolders. So I have to go into this one, and then 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 this one, and this one, and now I get my 3. And then I have to back out through each layer of that until I find all of the other options and then go into each of them. So it's a lot of work. And if I asked you to write this code, I know we haven't dealt with file systems yet. We're going to see that in a section here in a couple of weeks. But if I asked you to write this code, I think you can see this would be quite difficult to write. It's easy to say sum up how many files are in this folder, but how do you say and then do the same thing in every subfolder? Well, that's exactly what recursion is good for. I don't know how to answer the question, but I do know that if I can count all the files in this folder, and then I can tell you to count all the files in all of its subfolders, then boom, you'll get the answer and tell me how many files there are across the whole file system. And each one of those subfolders may cause more recursive calls, which will cause more recursive calls, which will cause more recursive calls. But it will eventually get there. So the cool part about this is it's actually very simple code. This is what the code looks like. And I'm waving my hand a little bit here because this isn't exactly Java code, but count files, it takes in a directory and it says, okay, the number of files is 0 to start with. I need you to count all of the files in this directory, which whatever that is, 7. And then I need you to add to that the count of all the files in each one of the subdirectories. So this is a recursive call that's going to check one subdirectory and get all of the files that are in it. And of course, it will cause another recursive call to get all the ones that are inside of it, which will cause another recursive call. And if you start this off with C colon or with slash, depending on whether you're Windows or Mac or Linux, then this is going to give you back the count of how many files are on your file system. This is really, really simple code. I'm kind of hand waving because I'm saying, well, just count the files in the subfolder. And it reads intuitively. Recursion generally will read very intuitively. And the other thing you'll notice is that most of the time when you write recursion, the code is going to be very simple. It's actually just a couple of lines of code. If you had to write this with a loop, it would be hundreds of lines of code. You'd have to keep track of every subfolder that you've been in and every subfolder that you haven't been in. And then you'd have to work your way through all of that. So the total amount of work to do here is it's very simply expressed recursively. Count all the files in the current directory and then recurse into each of the subdirectories and count in there. Whatever the sum of all that is, that's the answer to the question. All right, so let's take a look at another example. We're switching away from files and back to actual code. So this is another recursive method. I'm calling it do work. It takes in an integer I. It prints out the I, and then it says if the I is greater than 2, then there's a recursive call for I minus 1 and a recursive call for I minus 2. Okay, so this is the first time that you've seen a circumstance where there are multiple recursive calls. So how does that work? That just makes your head hurt, right? You've got two completely separate recursions that are happening in each method. So let's trace it. And again, the correct answer is not to panic and freak out. The correct answer is to realize that you just need to draw yourself a happy little activation stack and you need to trace it and not think too hard, and you'll get to the right answer. So we're going to draw our little red arrow at the top. We're in main. We're supposedly passing do work 4. I guess we're doing I equals 3 in main for some reason. And then what we're going to do is we're going to just trace it line by line. All right, so we're assuming that I is 3. And what we're going to do is the first thing that happens is we print out the 3. All right, so if I is greater than 2, which 3 is greater than 2, we're going to do work on I minus 1, which is 3 minus 1, which is 2. So that's going to make a new call, do work 2, and it's going to call I is equal to 2 in this version. So it says print out I, which is a 2 this time. If 2 is greater than 2, well, it isn't. 2 is not greater than 2. So this is going to jump to the closing curly brace and then do the print statement, which prints out another 2. And then it's going to move on to the closing curly brace, which ends that method. And we're going to go back to the previous version. Now, in the previous version, we were just doing this first recursive call. So now we got to do the second recursive call. So it's going to make a call to do work with I minus 2. In this version, I was equal to 3. So 3 minus 2 is going to be 1. So we're going to make a call with I equal to 1. In I equal to 1, we print out the 1. If 1 is greater than 2, it's not. So we're going to print out the 1 again, and we're going to end. Back down in the previous version, we just did the do work and the do work, the two calls. So now we're going to print out our I, which is equal to 3, and it pops off the stack, and we are done. So the output here is 3, 2, 2, 1, 1, 3, which is not at all intuitive. I want you to point out that if I had given you this code and you tried to guess what the outcome of this is going to be, yeah, you're never guessing that. And if you are, you're a wizard. So the chances are you have to trace the code, and that's building the activation stack and walking through it step by step and finding the answer. All right. So this brings us to Dr. Fibonacci. This was basically a mathematician, and one of the things that he studied was how rabbits reproduce. I presume he was a lonely man. So if you start off with 2 rabbits and you leave them in the field, and presuming that they are of sufficient genders to reproduce, then we will end up with 3 rabbits. And if we leave them in the field, we will then end up with 5 rabbits, and then we will have 8 rabbits, and eventually they will multiply like, well, they'll multiply like rabbits. So this is the Fibonacci sequence. It's an interesting mathematical formula, and it tells us this it grows very, very quickly, and it is based on rabbits multiplying. All right, let's move on quickly. So the way that the Fibonacci sequence works is if you ask for the Fibonacci of 0, the answer is 0. If you ask for the Fibonacci of 1, the answer is 1. And if you ask for the Fibonacci of 2, the answer is 1. So these are predefined numbers. Every other number in the sequence is the sum of the previous 2 numbers. So 2 is because you're adding the 1 and the 1 together. 3 is because you're adding the 2 and the 1 together. 5 is because you're adding the 2 and the 3. 8 because the 5 and the 3, 13 because of the 8 and the 5. That's how Fibonacci works. All right, so let's write some Fibonacci code. Over to our IntelliJ window, and so we're going to start off a new project again, and this one is going to be 4.3 example 3. Okay, so we start off and we have our main method. We're going to write a new method, public static. It returns an int. We're going to call it fib, and it's going to take in an int I, which is the number that we're trying to find the Fibonacci of. All right, so as I said, there's a definition in here, which is if you ask for the Fibonacci of 1 or you ask for the Fibonacci of 2, the answer is simply 1. So if I is equal to 1 or I is equal to 2, then return 1. When I write if statements, I always end up going back and putting the parentheses in because somehow it makes sense in my head. All right. In all other cases, Fibonacci needs to return the sum of the previous two numbers. So to say that in terms that are computer terms, I'm going to return the Fibonacci of I minus 1 plus the Fibonacci of I minus 2. Okay, now both of those are recursive calls. It's going to call the Fibonacci of I minus 1 first, get an answer for that. Then it's going to call the Fibonacci of I minus 2, get an answer for that, and then it's going to add it together. And that's it. All right, so let's test this. So int I equals, let's do 5. And we're going to say int answer is equal to the fib of 5. And then we're going to print out the answer. All right, let's run this guy. Let's see how many rabbits we have in 5 generations. Well, it says the answer is 5. So let's go back to our little chart. 1, 2, 3, 4, 5. Okay, so the Fibonacci of 5 is 5. That's kind of a weird fluke. So let's check Fibonacci of 7. That's a little bit bigger, and we would expect 6, 7, the answer to be 13. And there it is, 13. Now, let's add in a print statement here, just so that we can see each time it's called. I was called with I equal to I. All right, so every time fib is called, we're going to get that. So how many times are we going to see it? So again, I'm passing it in a 7, which is going to ask for the fib of 6 plus the fib of 5. How many times am I going to see this call? Well, let's run it. The answer is surprisingly a lot. So it was called with 7, then with 6, then with 5, then with 4, then with 3, then with 2, then with 1. And it stopped at 1 because it hit a terminating condition. But then on the other side, it started and it got 2, 3, 2, 1, 4, 3, 2. It's calling it a whole lot of times. Why is it doing so many times? Well, each one of these calls is recursive. So when I passed in a 7, that's going to answer fib of 7 plus fib of 6. So let's draw this out in an activation stack real quick so that we can see what's going on here. Oops, where is my window? Can't find my window. There it is. Okay. And I need to erase all of this. Okay. So in my Fibonacci sequence, what I'm always doing is I'm looking for the fib of the number before plus the fib of the number before that. All right. So I start off and I draw my happy little activation stack. And in main, I asked for fib of 7. So that called Fibonacci and it passed at 7. Well, looking at the code real quick, it said, is 7 equal to 1 or 7 equal to 2? It's not. So it returns fib of I minus 1. Well, I minus 1 is 6 plus fib of 5. Okay, well, it can't answer either of these directly, so it has to do one of them first. So it starts off with this fib of 6, which is a new call, and it says, is 6 equal to 1 or 6 equal to 2? It's not, so it's going to return the same thing. In this case, it's fib of 5 plus fib of 4. All right, and likewise, it can't answer that, so it's going to answer this one. So it's going to do fib of 5, and that's going to return fib of 4 plus fib of 3. And that's going to cause fib of 4. So that's going to return fib of 3 plus fib of 2. All right, and that's going to cause fib of 3, which is going to return fib of 2 plus fib of 1. Okay, so that's going to cause fib of 2, and now something different happens. If we go back and we look at our code, if I is equal to 2, return 1. So this simply returns 1. Okay, now where does that 1 go? Well, it is going to take this answer and it fills it in where it was originally asked from, which was fib of 2. So that's now replaced with the number 1. So on this layer of the activation stack, fib of 3, it now reads return 1 plus fib of 1. Okay, well, our previous layer of the activation stack is now done. So this is going to pop off. And when it pops off, what we're going to get is a call from the previous layer to calculate fib of 1. I erased the whole thing. Of course I did. I don't know why my pen is suddenly thicker. But anyway, details. So fib of 1. And again, we know the answer. That just returns 1. And that 1 is going to be filled in here. Okay, so when this pops off the activation stack, which it just did, because it's done, we're left with the fib of 3 reads return 1 plus 1, and that's obviously equal to 2. So this now answered, and where did it come from? It came from this original call right here. So fib of 3, the answer was 2. And again, this previous layer up on the top is done. So it pops off the activation stack. Now, in the fib of 4 section, yikes, we are now going to continue on with what it's left with, which is a call to fib of 2. And so that's going to cause a call to fib of 2, which is going to return 1. That 1 gets filled in, and now we have 2 plus 1, which is equal to 3. That 3 gets filled in here, and then we continue with fib of 3, and so on and so on. So I want you to understand here that it's not that one Fibonacci, it's not that one of the recursive calls keeps going until the end. It keeps going until it reaches a terminating condition. And then the previous layer wakes up and maybe makes the other recursive call if it needs to. And so you need to trace it very, very carefully. All statements in English are read from left to right, and all code is also read and executed from left to right. So when you have a return statement like this one down at the bottom here that says return fib of 6 plus fib of 5, it's first going to calculate the fib of 6, and it's going to get an answer on that before it ever thinks about looking at the fib of 5. The fib of 5 only comes up after it has answered fib of 6. So keep that in mind when you're tracing code, is that it's going to do it left to right. All right, so ultimately the Fibonacci sequence ends up looking like this. It's actually very simple code. I will warn you that if you try to calculate Fibonacci on any biggish number, it's just going to crash. This is wildly inefficient code, as you can see from the fact that it's calling the same methods over and over again. Like, look at how many times it asked for fib of 1. It doesn't remember that the fib of 1 is 1. It actually makes the call to fib of 1 each and every time. So that's a huge number of calls. And if I put in a large number here, like let's say 50, yeah, that's going to be running for a minute. So, yep, you can see the numbers are just changing down here and it is running. And I don't remember if 50 will actually give us an answer. We'll leave that chugging away here in the background while we're doing stuff. But it'll certainly take it a while to come up with that answer. Now, to be fair, part of the reason it's taking a long time is because of the print statement. If I were to take out this print statement on line 3, it will execute a lot faster. The print statement actually takes a while. That's why it's going so slowly. But still, I want you to see just how long this is running for. So we're going to go to the slides. We'll come back to this in a few minutes and see if we got an answer. All right, so the next topic we're going to talk about is a bubble sort. So in 1321, we talked to you about how you could take a list in that case, which is kind of their version of an array, and you could call .sort on it. And Python will very nicely sort the list for you and give it back to you. So at the time, we said it's useful to understand how sorts work because you might someday have to write your own sort. Most of the time, you're going to use the built in sort, but it's important to understand how sorts actually function. By the way, I can tell that the fan in my computer is spinning up because it's still busily calculating Fibonacci over there. All right, so let's take a look at a very small array. Well, now I would have said that I had erased that whole screen, and yet I obviously missed a bit up at the top. Let's erase that guy as well, and let's just draw a new array. So I'm going to start off with a smallish array. I'm just going to put in 4 cells. So cell 0, 1, 2, and 3. Yikes, that is off the screen for you guys. So let me move the screen. There we go. Okay, so I have 4 cells. I'm going to put in numbers. Let's do a 2, a 1, a 3, and a 5. Okay, so the question is, I want to sort this array. So in 1321, we mentioned an algorithm called a bubble sort. And what a bubble sort does is it takes a look at the first 2 elements in the array and it decides if they're in the correct order. So assuming that I want to sort this from smallest to largest, then no, these are not in the correct order. So if they're not in the correct order, then it goes ahead and it reverses them, which would put 1 here and 2 there, and then it moves on and it checks the next 2 values. If they're wrong, it sorts them, and then it checks the next 2 values. If they're wrong, it sorts them. So let's start off with an array that's actually much more unsorted, because this one was kind of already pretty close to being sorted when I started. So let's put in some, messed up numbers. So we'll do 4, 1, let's say 2, well, let's do 3, and then 5. Okay, so the bubble sort algorithm. We're going to check the 4 and the 1, and we're going to see if they need to be reversed. They do, so we're going to put the 1 in here and the 4 in there, and then we're going to move on to the next entry. The next entry is we're going to compare these two. So we're going to say the 4 and the 3, are they in the correct order? They're not, so we're going to reverse them. I'm going to put the 3 in here and the 4 in there. Then I'm going to move on, and I know you're looking at this going, it's sorted, stop, we're done. Yeah, the computer has no idea. So now we're going to check these two and make sure that they are correctly sorted, which they are. So yay, nothing to do there. Great. Now we have done the first pass. What we have accomplished in this pass is that we successfully got the largest item to the right-hand side. Now we have to do it all again, and I know, again, you can look at these numbers and see that they're sorted, but that was just by fluke of the numbers that I picked. The next thing it's going to do is it's going to check again the first 2 numbers, and it's going to see if they need to be sorted, then check the next 2 numbers. It doesn't have to check the last 2 because it already knows that this one is correct. So after it's done with that, this is now correct. And so then it's going to start checking these, and it might reverse them, and life is good. So if we take a look online here for a moment, let's take a look at this guy. So this is a kind of obnoxious little video, but it's here on YouTube. Let me explain what it's doing. So the height of each of these bars is a number, and let's assume that this is an array. Every time that you see something in red, that's it comparing 2 neighbors and switching them if it needs to. It's really only looking at 2. The fact that there's 4 highlighted is because I happened to pause it at a moment when it had drawn 2. But it's looking at the neighboring 2, and it's shuffling 1 number to the end. I'm going to go ahead and mute this, and let's run it again. So you can see that each time that it completes a pass, 1 element is correctly moved to the right-hand side of the array. And so effectively all it's doing is on each pass, where it passes it going all the way through the array, it's getting 1 number to the right place. And so it's going to get there eventually. In this case, all the numbers are evenly represented. So eventually you're going to end up with a nice smooth line here. But of course, they can be completely random numbers. So at the top here, it's keeping track of how many comparisons it did. This has done 2,000, 3,000, and it's had to access the array over 10,000 times already. And this is just with a array that has, I don't know how many there are in here, but maybe 100 numbers. Um, so as you can see, this is a huge amount of work that it's having to do, and it's still working away down there. Okay, now it's all sorted. So really what you want to learn from this is that a bubble sort, it does successfully sort the array, but it's not a really great way of doing it. And the reason that we mention it, like you might think, okay, why are we talking about this? Well, the reason we mention it is because it's useful to talk about how much work it takes to do a certain algorithm. And in this case, the bubble sort is considered to be an n squared algorithm. So what do I mean by n squared? Well, n squared means if the array has 4 elements, I will have to do 4 squared or 16 comparisons in order to sort the array. If the array has 100 elements, then I'm going to do 100 squared comparisons to sort the array. It's always going to be squared because that's the type of algorithm it is. And you might say, okay, why do I care? And what does this have to do with recursion? So, the reason that you care is because you're going to write a whole lot of sorting algorithms in your life. A very big problem in computer science is keeping things organized. Because when they're sorted, you can do cool things with them, like find the middle and know which item is in there. For example, if I wanted to know how many people in this class passed the last quiz, I would have to sort all of the scores for all of the quizzes, and then I'd look for everyone who got above 90 or above 70 or whatever threshold that I'm cutting it at. And so that's just an important detail, is that I have to be able to sort the list of scores. And that means I need an algorithm that sorts. And you say, well, okay, Java has a built in sort algorithm and so does Python. So why do I care? Well, how is it doing the sort is important because, again, the amount of work that it's going to take is going to tell you how slow your program is going to run. Think about it this way. If I ask you to sort an array that has 4 elements and it takes 16 operations, how long is that going to take? Well, it's going to take you 16 fractions of a millisecond. It's a tiny amount of work. But if I give you an array with 1.2 million elements and I ask you to sort it, and it takes 1.2 million squared operations to find the answer, then all of a sudden it's not quite so irrelevant. And you might say, well, when would I ever have an array with 1.2 million things? How many orders do you think Amazon gets per hour? It's probably in the order of millions. And they have to keep track of them, and they have to organize them and send them to the warehouse for pickup and so on and so forth. A lot of computer science deals with huge numbers. It's quite common that you're going to have to sort something with 100 million rows. And that's going to take, depending on the algorithm that you use, either it's going to take 15 seconds or it's going to take 3 weeks. And 3 weeks is not an acceptable answer. Think about it this way: if you're keeping track of items in a game, and every time you try to look at the items that you have in your satchel or your bag or your treasure chest or whatever it is, it pauses the game for 3 seconds. Are you going to be happy about that? No, no, you're not. You needed to do it much faster. So the speed at which it does the sort is very important. Okay, so having said that, a bubble sort kind of sucks. It's a very easy algorithm to write. As a matter of fact, if I were to write this code down for a bubble sort, it's just a nested loop. Very simply, I have an array and I simply say something along these lines. I'm just going to put a new method in here. By the way, still running on the subject of the order of speed of algorithms. Just want to point out that this entire time I've been talking, my Fibonacci is still calculating. All right, so we're writing our public static int bubble sort. All right, and it takes in an integer array, and we'll call it my array. All right, so the way that it works is we need a loop that goes all the way through the array. So for int I equals 0, I less than my array dot length. I would have thought it would have completed that, but it didn't. I plus plus. So that's one loop that's going to go through all the way. Now I'm going to write another loop that's going to do the sort along the way. So one loop does it how many times? however big the array is. And for each one of those passes, I need to move each element to the end. So for int j equals 0, j less than my array dot length j plus plus, I'm simply going to say if my array at position j is greater than my array at position j plus 1, then I need to swap them. So I'm going to need a temp. I'll call it temp. I'm going to set it equal to my array at position j. I'm going to set my array at position j equals to my array at position j plus 1. And then I'm going to set my array at position j plus 1 equal to temp. That's how you swap two numbers. You need a temporary variable to hold them. All right, so that's a bubble sort. This has a couple of bugs in it, and I'm intentionally leaving them in here. I just wanted to show you how to quickly write it. There are two bugs. One is there's an optimization. I don't have to go all the way to the length. I can go to the length minus I, because each time I've done an I, I've done one number into the right place, so I don't have to keep revisiting that. But that's just an optimization. But let's go ahead and add it in here. Minus I, which is my outer loop variable. And then the other problem that I have is j is being added 1 to it, but I'm going while j is less than the length. So let's assume there's 4 elements in my array. This loop is going to do 0, 1, 2, and 3. But when I'm at 3, this if statement is going to look at position 3 and position 4, which doesn't work. So I need to actually subtract 1 from all of that in order to stop it from doing that. All right. If I were to run this on a bubble sort, it would successfully sort it and I would get my answer. That's a bubble sort. You probably need to know that code and memorize it, because occasionally you'll get asked in an interview to sort something. And while a bubble sort is a terribly inefficient way to do it, it is a very simple algorithm to write. You just have to remember it's a nested loop with an if statement that swaps two elements. If you get that, you can chug your way through it and actually figure out the code. So it's a worthwhile thing to remember, but again, it's not really a very efficient algorithm. I'm missing a return statement here as well, because I said it returns an int for some reason, which I don't know why I did that, because it really produces a void. Okay, there we go. All right, so back over to our slides. That's the bubble sort. Definitely one you should remember. You will occasionally need to write a bubble sort, not because it's efficient, but because it gets the job done. And if you know it's a small amount of stuff, it gets there and it'll be fine. There are two other types of sorts that are also not great. These are called a selection sort and an insertion sort. Basically, a selection sort does the same thing as a bubble sort, but it does it in a slightly different way. It assumes that the first cell is the smallest value, and then it scans all the rest of the array to verify that it is the smallest. If at any point it finds a smaller number, whichever one is the smallest, it switches that into the first cell. Then it assumes the second cell is the smallest and checks all the other numbers. If it needs to, it switches them. And then it finds the third smallest and the fourth smallest and the fifth smallest. It's kind of doing the same thing as bubble sort, just kind of in the other direction. Either way, it's also considered an n squared algorithm. It takes n squared work in order to do it, and it's not great. An insertion sort is the third type. If you've ever played a card game where you have cards in your hand and they hand you a pile of cards that they've dealt, one of the first things you probably want to do is organize them so that they're in order. And so that's usually done with an insertion sort. Effectively, you take all of the cards and you pluck out the lowest valued one, and then you pluck out the next lowest valued one and the next lowest valued one, and at the end you have a sorted hand in your other hand. You're effectively moving them from one hand to the other. That's called an insertion sort. So you've used that in the real world as well. These also are good algorithms to know that they exist, but you're probably never going to have to write either of them. A bubble sort, you might actually need to write. Insertion and selection, it's worthwhile knowing they exist. All right, so I've said all three of these suck. So why do we still have them? Well, because that's the best that we knew how to do for sorting an array for many, many years, was n squared. It was believed that was the fastest way to do it. And it took a while for somebody to come up with something that was better than n squared reliably. And that's going to bring us to our next algorithm. So the next algorithm we're going to look at, as I mentioned, this is just the big O of things. The next algorithm we're going to look at is called a merge sort. I'm going to click this link that we gave you here in the slides. which is going to pop open something that's going to show how a merge sort works. So I'm going to ask it to produce an array with 8 elements in it. Okay, and they have random values. So this is how a merge sort works. Basically what happens is I'm going to take the array and I'm going to split it into 2 separate arrays that are each half the size of the previous one. And then I'm going to keep doing that recursively until I get down to an array that's a single cell. So I'm going to split each of those in half, and I'm going to split each of those in half, and now I'm down to a single cell. Once I'm at a single cell, we know that I'm already sorted, so I don't have to worry about sorting. So now what I'm going to do is I'm going to merge these back together again in the correct order. So the way that I do that is I take both of these and I look at them and I decide which is the smallest, which is 303. I move that into cell 0 of the parent. Then I take the next size and I move that into the parent. So it turns out these are already sorted, so I'm going to put them back in the same order, but they're now a sorted array. Okay, now I'm going to do the same on this side. So I'm going to take the 759, I'm going to break it into 2 halves, I'm going to clear out the parent, and then I'm going to pick the smallest one, which is 665, and put it in cell 0, and then pick the next smallest one, which is 759, and put it up there. Okay, at this point, I have 2 sorted arrays. So now I'm going to merge them into this array. Clear out the parent, and I'm going to look at the first cell of each of these 2. I know that both of these subarrays are already sorted, so I just have to look at the first cell in each one. So between the 303 and the 665, the 303 was the smallest, so I move that up. Now I'm looking at the 665 and the 764. The smallest of those is the 665. Now I'm looking at the 764 and the 759. The smallest of those is the 759. And then finally, I need to move up the 764. Now this array is sorted. Okay, now I need to repeat the whole same thing again over here. I'm going to take this, I'm going to break it in half, I'm going to break each of them in half, and then I'm going to sort them, so 596 and then 602. Now I'm going to repeat the same thing over here, break them in half, and I'm going to sort them so that I get 23 and 248. Okay, let's talk through the merge one more time. So again, I clear out this array, and I start off looking at cell 0 here and cell 0 here, and I find the smallest of the 2, which is this 23. I'm going to move that up, then I'm going to move this over to cell 1 because I've used cell 0. Then I'm going to compare cell 0 here and cell 1 here. So again, the 23 and the 596, the answer is 23. Now I'm looking at the 596 and the 248. The answer is 248. Now I'm looking at the 596 and the 602, and I know that that's in the correct order because I've already guaranteed that. And then finally, we repeat this same step up at the top. So I clear out the array, and I look at the 23 and the 303. That's going to be 23. Then I look at the 248 next. Then I look at the 383 next, or sorry, the 303 next. Then I look at the 596 next. Then I look at the 602 next. And then I just need to copy all the rest of this array up because we know we're done with this array. So it's just copy, copy, copy the remaining cells. And as you can see, at this point, the top array is now correctly sorted. You can see at the bottom here, it tells me that that took 96 steps. And you might say, well, that's pretty inefficient. Let's take a look at the size of this array. It looks like this had 8 elements. So what's 8 squared? Yeah, it's 64. So yeah, this wasn't any faster than a bubble sort. Would have been pretty much the same amount of work as a bubble sort. Let's do a much bigger number. Well, it won't let me do a much bigger number. Okay, what I'm going to tell you is that the way that you calculate the amount of work that we're doing here is that there were 2 phases in what I was doing. If I start back at the very beginning again, the first phase was me splitting the array over and over and over into smaller subsets. Then there's the part of merging it back together again. So phase 1, splitting it, phase 2, merging it back together. All right, the amount of work it takes to merge, let's do the merge part first, is n, because I have to look at every element and copy them up. So if there's 2 cells, it's going to be 2 work in order to move them up. So the merge is an n. But the splitting part, every time I split it, I'm dealing with half as many arrays. So it's called a log n amount of work to do the split. So in actuality, it's log n work to do the split and n work to do the join, and I have to do one join for every split. So therefore, it's n times log n, or as we would call it, n log n. Now, first off, when we say log, we're dealing in log base 2. We're not dealing in log base 10 because binary. We're splitting something in half, so therefore we're getting half of the work each time. So merge sort, which is the name of this algorithm, is considered to be an n log n algorithm. And you might say, isn't that terrible? And well, the answer is it's not great, but it's certainly better than n squared. N squared is a lot more work than n log n. And so if you put in a large number of cells, like 1,000,000 cells versus 100 million cells, all of a sudden you're going to notice a big difference between a bubble sort, which is n squared, and a merge sort, which is n log n. It's going to be significantly faster. So let's take a look at this algorithm. So as we saw, you take the array, you split it, you keep splitting it until you get to individual cells, you merge them back together again, you merge these back together, you merge those back together, and then you do the same on the other side and you merge it all back together again in the end. So there are two parts. There's the merge sort algorithm, which is what's doing the splitting, and then there's the merge algorithm, which is doing the join, and they're two separate methods. So let's take a look at the merge sort. It takes in an array and it takes in an int n, which is the size of the array. This is going to change each time we call it because we're going to have the full array, then half the array, then half the array, and so on. So if n is greater than 2, i.e. if there's more than 2 cells, then you're going to return. If it's less than 2, meaning if there's one cell, you're going to return because we can't split one cell. I'm going to say that all again because I fumbled over those words. If n is less than 2, meaning if n is 1 or 0, we're done splitting, so just return. All right. Otherwise, we're going to figure out where the middle is. So we take n, which is the size, we divide it by 2. That tells us where the middle is. And then we're going to make a left array and a right array. The left array is the size up to the middle, and then the right array is n minus the middle. And you might say, isn't it just middle and middle? It is, but there could be an odd number of cells. If you have 13 cells, then you're going to put 6 on one side and 7 on the other. That's why you have this n minus 1. And then we just simply need to copy the data over into those two arrays. So all this code really here is doing is the split operation that you're used to in Python. So I'm just making a left array, I'm making a right array, and then I'm copying the data into the left array and copying the data into the right array. After I've made the two left and right arrays, I simply call merge sort, which is the name of the method that I'm currently looking at, with the left array and the size of the left array, and the right array with the size of the right array. So this is saying take the full array and then call merge sort on the left side and call merge sort on the right side. And that's going to keep going until you're eventually down to an array that has one element. After you're done with calling left and right with merge sort, you're then going to call merge, and you're going to pass it a whole bunch of things. You're going to pass it the full array, that was the original array that we got, the left array, the right array, the size of the left array, and the size of the right array. Okay? So here's our merge code. It takes in all of those things, the full array, the left array, the right array, the size of the left one, the size of the right one. And all it's doing is what we described in that code where we're merging these numbers back together into the children, from the children into the parent. So you're taking the smallest of the two numbers and you're copying it down, and then you're looking for the next smallest, and then the next smallest, and the next smallest. Knowing that these two arrays are already sorted, you can accomplish that by this. So while I is less than left and j is less than the right, then if the one on the left side, is less than the one on the right side, then into the full array, add the left side. Otherwise, add the right side. And then once you've done hitting the edge of either the left array or the right array, just copy all the rest of the other two arrays over because we know that they're already sorted. That's the merge. So it's not a particularly difficult piece of code, and it is way more efficient. And to be clear, this, or a derivative of this, is how most algorithms are actually using sorts today. So if you call array.sort in Java, you're actually getting a quick sort, which is a derivative of a merge sort. It's very similar to merge sort with just one slight change. Likewise, in Python, you get a very similar algorithm. So merge sort is the foundation of how sorts are done nowadays. As I say, there's a couple of variations of merge sort, and depending on the type of data that you have, one of them may be slightly more efficient than another. So generally, it takes a look at them and then it decides which one to call. But for the most part today, they use quicksort, which again is basically merge sort with one minor change. And you can look that up if you want to take a look at a Wikipedia page or do a quick search on how is quicksort different from merge sort. You'll see the answer online. All right. So what I'm telling you here is that this had two recursive calls in it. If we go back to the merge sort function, it calls merge sort twice, once with the left side and once with the right side. Much like Fibonacci, you had two recursive calls. So is that as bad as it gets? Is there ever any circumstance where you have more than two recursive calls? Well, the answer is yes. You can absolutely have three, four, or even more recursive calls. So let's take a look at another problem. Let's imagine you're in a maze or you're in a room and you're trying to explain to the player how to get out of the room. Let's take something like a Roomba or a little robotic vacuum cleaner or something like that. In order to get out of a particular room, if it doesn't know the path, it's going to have to figure out the path. And so, generally, the algorithm that it's going to use is you're going to check for some base conditions. Are you where you're trying to get to? If you are, you're done. Yay. If you're not, are you currently facing a wall? Because if you're currently facing a wall, you can't really go that way. You need to turn around and go the other way. Have you ended up somewhere that you've already been? So if you go into a room and you're like, I've already been in this room, there's no point in researching the room. You know that you've already been through that room. So you've got three base conditions that are going to stop your recursion. You've gotten where you're going, you've hit some kind of a wall or an obstacle, or you're somewhere that you've already been. In all other cases, the algorithm is very simply recurse to the left and see if that gets you there. If it doesn't work, recurse to the right and see if that gets you there. If that doesn't work, recurse forward and see if that gets you there. And if that doesn't work, recurse backwards and see if that gets you there. And each one of those recursive calls is going to check these conditions up at the top. And this is an example of a very simple algorithm that will do a full search of a very large organization. So, what I mean by this is if you've ever played a game and there's a player that's moving around, the chances are it's going to be running something like this. Because the board is generally dynamically created, the surface that the players are playing on, you don't know whether there's going to be a wall somewhere or whether you're going to have to do something. So the algorithm that it follows is this. This is also the algorithm that your Roombas and your robotic lawnmowers and any kind of robot that you have is following basically as well. Try going one way. If it doesn't work, try going the next way. If that doesn't work, try going the next way. And you could certainly have a circumstance where there's 8 recursive calls if you're allowed to go diagonally. This is assuming you can go left, right, backwards, and forwards, but you could also have northeast, northwest, southeast, and southwest. That would be 8 recursive calls, or 16 recursive calls, or 32, or 64. It doesn't really matter. You can certainly have any level of recursion that you might need. But 4 is a pretty common circumstance. Any kind of maze solving problem, any kind of mouse looking for a cheese kind of thing, you're going to have that. And as a matter of fact, most mapping programs do this very same algorithm. If you type into your Google Maps or your Apple Maps that you want to go to a particular store, it looks up the address of the store, it figures out where you are, and then it follows an algorithm that basically says, try going right and see if that gets you there. If that doesn't work, try going left, see if that gets you there. And if that doesn't work, try going forward, see if that gets you there. And that's kind of how it recursively figures out the answer. So recursion is really used in the real world. That's a very important detail here. It's not some abstract thing. Yes, for the simple problems that we gave you at the beginning of this, it's a very abstract thing that really people don't use very often. But as far as what we're looking at here, this is a real thing. Mapping software, searching any kind of a maze, going through any kind of checking various different boards in a board game and looking at each board and deciding is that the best board or the worst board. Most of those algorithms are recursive. You try one thing, if it doesn't work, you try another. The first chess solvers, if you're familiar with chess, worked this way. Try moving a pawn forward and then see what the player will do in reverse. The actual algorithm there is called min-max, and that's a very common algorithm that's used for automatic game playing. Tries to make one move and see what the counter move is, and then make another move and see what the counter move is, and keep going until you win the game. And if that doesn't work, then try a different move. And if that didn't work, then try a different move. And if that didn't work, then try a different move. All of those are recursive because in each case, the different boards that you can be in continue on. So recursion is really useful. It's really something that we use in the real world. When you deal with something that is nonlinear, and all those last examples are nonlinear mapping, searching a maze, finding the different options in a board game, all of those are nonlinear because each move gives you a whole new array of new moves that you could do. And so those are all going to be recursive algorithms. So very important that you do this. Again, as we wrap up this section, I will say this is going to have made sense when you're watching the video, hopefully. But when you sit down and try to do it, you're going to find this part challenging. It's a really different way of thinking. When I took my class a million years ago, my professor said, in order to understand recursion, you need to take out your brain, turn it around, put it back in again, and then it's all going to make a whole lot more sense. And yeah, that's kind of where we are here. You kind of have to just try it for a while, and I promise at some point it will make sense. And then once it makes sense, you'll see it's actually really elegant and kind of beautiful. I know people say that about math, and you're like, ugh, math. But it really is kind of beautiful. It's a really simple algorithm, and it produces really complex results. And a whole lot of what you use today in gameplay, in problem solving, in mapping, and all of these algorithms, a lot of them are recursive in nature. So it really is something you need to understand. These are some more examples that are here at the end that you can certainly try. Obviously, you can use a chat GPT or something to produce you an answer if you don't get to an answer, but I would encourage you to try each of these up front and see if you can come up with an answer. There are no answers in the slides because, again, you can just look up an answer to each of them. But these are good things that you can practice with. One of them we just did in class, but all the rest of them are new. Okay, well, that completes our lecture today on recursion. I will see you guys in the next class where we will talk about exception handling.